Hey everyone, sometimes a single question can stretch across the entire universe. Ours begins not with a discovery, but with a young astronomer standing before a blackboard in 1961, sketching out a formula that would change the way we think about life beyond Earth. The place was the Green Bank Observatory in West Virginia, a quiet valley, shielded from the static of radio transmissions, chosen so the giant dish telescope nearby could listen, with as little interference as possible. That November, 10 scientists gathered there for what was called the first conference on the search for extraterrestrial intelligence. Before we get into what happened in that room, think about the weight of the question they were facing. For the first time in history, scientists were trying to put a shape around the mystery of other civilizations. Imagine being one of them, sitting in that quiet valley in 1961, asked to put a number on it. How many civilizations do you think are out there, right now, sending signals into the dark? I'd love to hear what you think. Leave your thoughts in the comments, and we'll see how your instincts compare to the ideas that were being debated that week. Because what they were really doing at Green Bank wasn't about solving anything, it was about daring to ask the question out loud in a serious way. It is difficult today to understand how bold that was. In 1961, the space age was still in its infancy. Yuri Gagarin had only just become the first human to orbit Earth. John F. Kennedy had promised that Americans would walk on the moon before the decade was over. There was excitement, yes, but also deep uncertainty. Nobody had yet discovered a single planet around another star. Most astronomers assumed they must exist, but there was no evidence. The idea that planets were common was speculation. The idea that life might be out there was little more than philosophy. Yet Frank Drake, just 31 years old, had already tried. The year before, in 1960, he had pointed a radio telescope at two nearby stars, Tau Ceti and Epsilon Eridani, and listened. He named the experiment Project Ozma after the princess in The Wizard of Oz because it felt like looking for a fairy tale kingdom. For 150 hours, the telescope strained through static, searching for a narrowband signal, something so unnatural it could only be artificial. Nothing came back. To some, the silence was anticlimax, but to Drake, it was progress. The odds of success had been vanishingly small. Listening to only two stars for a few weeks was like dipping a cup into the ocean and declaring it empty because it came up dry. The point wasn't to find a signal. The point was to prove we could try. Project Ozma marked the first time humanity had aimed a tool at the sky specifically to listen for intelligence. In that sense, it was a breakthrough. The Green Bank meeting was the next step. Drake wanted to transform the question from idle speculation into something science could at least frame. He knew he could not answer whether civilizations existed, but he could break the question down into pieces that could be discussed, debated, and eventually measured. When the 10 scientists settled into their chairs, Drake went to the blackboard. He sketched out a string of terms, not an equation in the mathematical sense, but a framework. Each term represented a stage in the journey from star to civilization. How many stars are born each year in the galaxy? How many of them have planets? How many of those planets might be habitable? How often does life arise? How often does life become intelligent? How often does intelligence produce technology capable of sending signals? And then came the final piece. How long do civilizations last once they begin to broadcast? The room quieted at that. Everyone understood the implications. Because while the earlier steps could be guessed at optimistically, stars are common, planets probably are too, life might emerge readily. The question of longevity was different. It was not just about them out there. It was about us, here and now. How long would humanity survive? Would we last long enough to fill the galaxy with signals? Or would we vanish quickly, leaving only a faint bubble of noise that expanded for a short while before fading forever? The timing of that meeting made the question even sharper. Just a few hundred miles away in Washington, D.C., nuclear weapons were being stockpiled in numbers large enough to erase civilization many times over. For the first time, humanity had the power to destroy itself. The paradox was glaring. The same technology that allowed us to reach out to the stars also gave us the means to silence ourselves. This was 1961. The Berlin Wall had just gone up. The Cuban Missile Crisis was only a year away. People lived with the quiet knowledge that a siren could sound at any moment, signaling the end. And here, in a quiet valley in West Virginia, 10 scientists were wondering whether civilizations anywhere ever made it past this stage. Carl Sagan, not yet famous but already restless with curiosity, leaned forward as Drake spoke. Otto Struve, older and more skeptical, considered each term with caution. The others scribbled notes, debated, offered guesses. But when they reached the question of longevity, nobody could give a confident answer. Some thought civilizations might endure for millennia. Others suspected they might barely last a century. The truth was that everything depended on that last variable. If civilizations endure for millions of years, then the galaxy should be filled with signals, a network of voices spanning the stars. But if they survive only briefly, then silence is what we should expect. The galaxy could be full of civilizations, each one shouting for a moment, then falling quiet long before anyone else could hear. That realization carried a weight that was hard to ignore. The Drake equation, as it came to be called, was not just about aliens. It was about fragility. It was about survival. It was about the mirror it held up to our own species, reflecting back the question of whether we would last long enough to be noticed. The scientists left Green Bank without answers. The chalkboard was erased. The telescope outside continued to listen, steady and patient. But the conversation had changed everything. For the first time, the question of extraterrestrial life had been framed in terms science could pursue. And for the first time, humanity had to confront the possibility that the answer depended less on others and more on ourselves. What makes this story so compelling is not that it gave us numbers, but that it forced us to think about what those numbers meant. Stars and planets are statistics, but survival is personal. Longevity is personal. It is the measure of whether we will be one of the civilizations that endure, or one of the countless that flicker and vanish without ever being heard. In that sense, the Drake equation is less about astronomy than about perspective. It asks us to imagine ourselves not just as a species on Earth, but as one voice in a galaxy of possible voices. It asks us to think about time not in centuries or millennia, but in millions of years. And it asks us to face the uncomfortable truth that our own choices will determine whether we last long enough to participate in that larger conversation. As we look back on 1961, it feels almost poetic. Humanity had just begun to leave Earth, to orbit the planet, to imagine walking on the moon. At the same time, it had built the capacity to destroy itself. Into that tension walked Frank Drake, with a piece of chalk and a question. How many others are there? The courage of that moment was not in finding an answer, but in admitting we did not know, in daring to wonder aloud, in refusing to dismiss the question as unworthy of science. For all its uncertainties, the framework Drake sketched on the board was a declaration. The question of whether we are alone is a question worth asking, and that is where the story begins. With a young astronomer, a chalkboard, 10 scientists in a quiet valley, and the recognition that the greatest mysteries are not solved in a day. They are framed, they are asked, and they are carried forward, generation after generation, waiting for voices that may or may not come. Because in the end, the silence of the stars is not only about them, it is about us. Once the chalkboard in West Virginia had been erased, and the scientists had gone home, the question they left behind began to ripple outward. If stars give rise to planets, and if some of those planets host life, then surely the galaxy should not be quiet. The challenge was to listen. The challenge was to speak. The truth, though, is that Earth had already been speaking for decades. It just hadn't meant to. From the late 1930s onward, our planet began leaking signals into space. Radio towers sprayed energy in every direction. Radar pulses designed to sweep the skies for aircraft or missiles blasted far beyond their targets. These signals were strong enough to escape the atmosphere, racing outward at the speed of light. A bubble of noise began to grow around Earth, expanding year by year, carrying with it the first faint fingerprints of a technological species. What those signals revealed about us was complicated. They were not messages carefully chosen to represent humanity. They were accidental, messy, chaotic. To a distant listener with sensitive instruments, Earth would not appear first as a planet of music or greetings. It would appear as a planet alive with pulses, alarms, and surveillance. Our first and loudest announcement to the cosmos was not an introduction, but the echo of our own unease. Yet that bubble, for all its imperfections, was extraordinary. For the first time, a planet that had been silent for billions of years was suddenly visible. If someone happened to live around one of the 1,000 stars within 100 light-years of us, they might be able to detect it. They would know that, at least for a moment, Earth was loud. But accidental leakage was never going to satisfy human curiosity. If we could be detected by accident, then surely we could also choose to speak on purpose. That decision came in 1974 at the Arecibo Observatory in Puerto Rico. The telescope itself was an engineering marvel, a dish 1,000 feet across, nestled into a natural sinkhole, its surface gleaming under the tropical sun. Usually it was a listener, gathering faint radio waves from pulsars and galaxies. But on one November day it became a transmitter. The target was the globular cluster M13, a dense sphere of hundreds of thousands of stars located 25,000 light-years away. The scientists knew perfectly well no reply could ever come. Even if someone received the message instantly and answered right away, the round trip would take 50,000 years. The choice of target was symbolic, a gesture toward a place rich with suns, a cluster where life might have found footholds many times over. For 3 minutes, the telescope beamed a powerful signal into space. Encoded in binary, it carried a message about who we are. Numbers, simple and unmistakable. The atomic numbers of hydrogen, carbon, nitrogen, oxygen, phosphorus. The building blocks of DNA. A sketch of the double helix. A human figure. The outline of our solar system, with Earth highlighted. A depiction of the Arecibo telescope itself. It was in a sense a postcard, a self-portrait carved in radio waves. Not meant to start a dialogue, but to mark a moment. Humanity declaring, we exist, and we have thought about the possibility of being known. Looking back, it's hard not to feel the poignancy of that gesture. Here we were, a species still fumbling with its own survival, already daring to send our likeness to the stars. It was a statement of confidence, but also of vulnerability. A message sent not because we expected an answer, but because we could not resist the impulse to reach outward. As we were sending, we were also beginning to learn. For decades, astronomers had suspected that planets must be common, but direct evidence was lacking. In 1995, the first planet orbiting a sun-like star was confirmed. A massive gas giant skimming close to its parent sun. Strange, unexpected, but proof that planets existed beyond our own system. Then came Kepler. Launched in 2009, the Kepler Space Telescope stared at a patch of sky in the constellation Cygnus, monitoring the brightness of more than 150,000 stars. It was designed to catch transits, the tiny dips in light that occur when a planet passes in front of its star. By measuring these dips with exquisite precision, Kepler revealed worlds that had been invisible. What it found stunned us. Thousands of planets, orbiting stars near and far. Planets larger than Jupiter, smaller than Earth, some scorched, some frozen, some in the temperate zones where liquid water could flow. Kepler's discoveries transformed the numbers in Drake's equation from speculation into certainty. Planets are not rare, they are the rule. Among them were worlds that stirred the imagination. Kepler 22b orbiting in the habitable zone of its star, where oceans might exist. Kepler 452b orbiting a sun-like star at nearly the same distance Earth circles ours, a potential cousin across space. The TRAPPIST-1 system, a dim red star surrounded by 7 rocky worlds, 3 of them within the habitable zone. Imagine standing on one of those planets and seeing 6 other Earth-sized worlds hanging in the sky, close enough to fill the horizon. The message was clear. The galaxy is filled with real estate. Earth is not unique. If life begins easily, then the odds are overwhelming that it should have begun many times. The stage is set for a galaxy alive with biology, intelligence, and culture. And yet, the silence continued. There was one moment, however, when that silence cracked, at least for 72 seconds. In August of 1977, at the Big Ear Radio Telescope in Ohio, astronomer Jerry Eman was scanning the incoming data. The computer printed numbers and letters representing the intensity of signals. Usually the pages showed nothing unusual, just static, a flat sea of randomness. But suddenly, on one page, a column of characters rose dramatically above the rest. It was narrow, strong, and lasted just long enough for the telescope's beam to sweep across it. Emmons circled the spike in red and wrote a single word. Wow. The wow. Signal has never been explained. It was at the right frequency, the one researchers had long suspected might be chosen by others, near the emission line of hydrogen, the most abundant element in the universe. It was narrowband, exactly what a deliberate signal should look like, but it never repeated. Every effort to find it again failed. To this day, it remains the most tantalizing anomaly in the history of the search. Some suggest comets, satellites, or natural sources. Others hold out hope that it was a true signal, a fleeting glimpse of another voice. The frustrating truth is that with only one instance we cannot know. But the wow signal endures as a reminder of how fragile the evidence might be. A whisper in the dark, here and gone, leaving us to wonder forever. Meanwhile, our own bubble of detectability keeps expanding. Today it stretches about 100 light-years in radius, a sphere of noise filled with radio, radar, and broadcast history. Inside that bubble are perhaps a few thousand stars. Outside it are hundreds of billions more. The scale is staggering. The galaxy is 100,000 light-years across. Our bubble is 100. We have reached only the smallest corner. To anyone beyond it, Earth is still invisible. To anyone within it, our presence is faint, our signals thin and fragile against the cosmic background. Even nearby, reconstructing their content would be nearly impossible. What remains detectable are only the strongest bursts, the deliberate transmissions like Arecibo, or the enormous radars of the Cold War. This reality reframes the silence. Perhaps we should not be surprised that we hear nothing. We have barely begun to listen, and our own shout is still small. Expecting a reply after only a few decades may be as naive as expecting an echo in a canyon after speaking a single word, and yet, the paradox lingers. Because if civilizations are common, and if they endure, then signals should overlap. They should be part of the background, obvious and undeniable. The fact that they are not forces us to consider that either civilizations are rare or fragile or speaking in ways we do not yet know how to hear. The silence is not empty, it is charged. It carries with it the weight of possibilities, each one unsettling in its own way. But still, we keep listening. The Allen Telescope Array points its dishes skyward. Breakthrough. Listen scans 1,000,000 stars. Data pours in. Endless noise waiting for a pattern. Each scan is a reminder of how vast the haystack is, and how patient we must be to find even a single needle. Perhaps the silence is only temporary. Perhaps we are still too early. Or perhaps we are misinterpreting what we see, mistaking signals for noise, overlooking what is right in front of us. Whatever the case, the search itself has become part of our identity. Because even in the absence of answers, the act of listening is its own kind of signal. It declares that we care, that we are curious, that we are willing to wonder, even if the wondering never ends. The stars are not silent. They blaze, they pulse, they flare. They host worlds without number. They carry the possibility of life written in their light. But when we search for voices, for intention, for others like us, the silence presses back. It is in that silence that we find the mystery, and in that mystery that we find ourselves. If the stars give us the stage, the next question is whether life ever steps onto it. For centuries, many assumed Earth was unique, a singular oasis in a silent universe. But as we've learned more about biology and about the astonishing resilience of life, that assumption has grown harder to defend. The story begins, in a sense, at the bottom of the ocean. In February of 1977, a small research submarine called Alvin descended into the darkness of the Pacific, near the Galapagos Rift. Scientists expected to find very little there, just cold blackness and a barren sea floor. Instead, they stumbled upon something that reshaped our understanding of life itself. Around the hydrothermal vents, where boiling water rich with sulfur spewed from cracks in the earth, were entire ecosystems thriving in what should have been a death zone. 8-foot-long tube worms, giant clams, blind crabs, and countless microorganisms lived not on sunlight, but on the chemistry of the vent. Life, it turned out, did not need warmth from the sky. It could build an entire food web in the darkness, fueled by minerals and heat from the Earth's interior. This discovery sent shockwaves through biology. If life can adapt to boiling sulfur pits at the bottom of our own oceans, then why couldn't it arise in the dark oceans of distant worlds? Suddenly, moons like Europa and Enceladus, once dismissed as frozen wastelands, became promising candidates. Beneath their icy crusts lie oceans larger than all of Earth's seas combined, kept liquid by tidal forces and internal heat. In complete darkness under miles of ice, there could be vents just like the ones Alvin explored, and perhaps ecosystems just as strange. Even within our own solar system, signs hint at the possibility. Mars, once a dry, dead planet in our imagination, now shows scars of ancient rivers, floodplains, and perhaps even shallow seas. Meteorites from Mars, blasted into space by impacts and later found on Earth, have shown curious structures, tiny shapes that some claim resemble fossilized bacteria. The evidence is debated, but the mere possibility keeps the question alive. And then there are the geysers of Enceladus, shooting plumes of water vapor and organic compounds into space. When the Cassini spacecraft flew through one of those plumes, it detected complex molecules, the building blocks of life. Imagine that. An ocean world hidden beneath ice, advertising itself with fountains of chemistry visible from space. If life ever took hold there, it might not be locked away forever. Its signature could be drifting in those plumes. What we've learned from our own planet is that life begins quickly when conditions allow it. Earth cooled enough for liquid water about 4 billion years ago. And almost immediately afterward, as soon as the planet was habitable, life appears in the fossil record. Not complex life, of course, but microbes, bacteria, simple forms. That speed suggests that once the stage is set, life does not hesitate to emerge. And yet, there's a catch. While life began quickly, intelligence did not. For nearly 4 billion years, Earth was ruled by microbes. Whole continents shifted, mountains rose and crumbled, oceans opened and closed, and through it all life remained mostly microscopic. It wasn't until about 600 million years ago that complex multicellular organisms began to thrive. Then, about 540 million years ago, something extraordinary happened: the Cambrian explosion. In a geologic blink, life diversified into an astonishing array of forms: trilobites, sponges, worms, the ancestors of nearly every modern animal. Why did it take so long? And why, once it began, did it accelerate so quickly? Scientists still don't fully understand. Some point to rising oxygen levels, others to genetic innovations, still others to environmental triggers. But the mystery remains. Why did Earth's biosphere wait billions of years before blooming into complexity? That long delay raises an unsettling thought. If life arises quickly but remains microbial for most of its history, then perhaps the galaxy is full of worlds covered in oceans and slime, teeming with cells but devoid of minds. Civilizations might be rare not because life is rare, but because the leap from microbe to mind is long and uncertain. Even on Earth, intelligence is a slippery concept. Dolphins communicate with whistles and clicks that suggest a kind of language. Octopuses use tools and solve puzzles. Certain birds display reasoning that seems astonishing for their small brains, and yet only one species developed the ability to build radios, telescopes, and starships. Only one species sits awake at night and asks, "Are we alone?" This raises another possibility. Intelligence may not be inevitable. It may be an accident, a quirk of evolution rather than its destination. If so, then civilizations might be rare not because the universe is hostile, but because it doesn't particularly favor minds like ours. Still, the fact remains, we are here. Out of microbes, out of chance, out of countless evolutionary experiments, one lineage on one planet began to think beyond itself. That alone is worth reflecting on. And it forces us to confront the role of time. Earth has been habitable for about 4 billion years. Civilizations capable of communication have existed for only about a century. If intelligence is common but short-lived, then civilizations may flicker on and off like fireflies in the night. For two to overlap, for us to hear another, or for them to hear us, requires extraordinary timing. It's almost like standing in a vast desert with a lantern, hoping that another wanderer also happens to be carrying a lantern, and that both lights happen to be on at the same time, pointing in the right direction. The odds feel slim, and yet the desert is vast and the night is long. When scientists at Green Bank debated the factors in Drake's formula, this was the part that carried the most weight. They could imagine stars and planets in abundance. They could imagine life arising wherever conditions were right. But when it came to intelligence, and especially to longevity, the mood grew quiet. Because intelligence is fragile, civilizations are fragile, and survival is never guaranteed. This is why discoveries like extremophiles, organisms that thrive in boiling acid, frozen ice, or radioactive waste, are so inspiring. They remind us that life itself is tenacious, it adapts, it endures. If microbes can survive the harshest corners of Earth, perhaps they can also survive on distant worlds. But tenacity at the microbial level does not always translate into endurance at the cultural level. Imagine a galaxy where life blooms easily, but civilizations flicker out quickly. 1,000 planets with oceans, but only a handful where minds emerge. And among those few, only some survive long enough to speak across the stars. That vision is haunting, but also strangely beautiful. It suggests we may be part of a pattern much larger than ourselves, a pattern of beginnings and endings, sparks and silences. And perhaps that is what makes the search so compelling. We're not just asking whether life exists elsewhere. We're asking whether other minds have looked up at their own night skies and wondered the same thing. Whether they too passed through long ages of silence before finally inventing the tools to reach beyond their world. Whether they too struggled with survival once they gained the power to end themselves. When you think about it that way, the question isn't only scientific, it's personal. It's a mirror held up to our own history. Because every time we ask if life is common, we're also asking how rare we are. Every time we ask if intelligence is inevitable, we're also asking if our own intelligence is a fluke. Every time we ask how long civilizations survive, we are really asking whether our own story will be long or short. This is why the discoveries of the last half-century matter so much. Hydrothermal vents, Europa's ocean, Enceladus's geysers, Mars' ancient rivers. Each one expands the space of possibility. Each one whispers that life might not be confined to this fragile dot in space. And yet, all of them also remind us how difficult it is to climb from chemistry to culture, from cells to civilizations, from whispers to songs loud enough to cross the stars. When Frank Drake wrote his framework on the board in 1961, this was the part that unsettled everyone. Not the abundance of stars, not the likelihood of planets, but the leap from simple life to complex minds. Because in that leap lies the difference between a galaxy full of silence and a galaxy alive with voices. It's worth sitting with that thought for a moment. The universe may be generous with life, but stingy with minds. The cosmos may be full of oceans and microbes, but almost empty of civilizations. And if that is true, then our existence becomes all the more precious. Against all those odds, we are here. For the briefest moment, we are not silent. We are broadcasting, we are listening. And perhaps, somewhere, someone else is doing the same. By the middle of the 20th century, Earth had begun to change its relationship with the cosmos. For almost all of its 4 billion-year history, our planet had been quiet to the wider galaxy. The sun's light reflected from oceans and clouds, but there were no signals, no signs of intention or intelligence. Then, within the span of a single century, that silence ended. The change began almost accidentally. Radio towers rose across cities, pouring energy into the sky. Radar stations scanned for airplanes and later for missiles, their beams spilling far beyond their targets. Satellites relayed communication, transmitting with a power that escaped Earth's atmosphere. Without meaning to, humanity became detectable. A bubble of noise began expanding outward at the speed of light, carrying with it the first faint evidence that intelligence had appeared on this small world. What those signals revealed was complicated. They were not the careful greetings of a species ready to introduce itself to the universe. They were the messy byproducts of our daily lives. Music and news, chatter and warnings, entertainment and alerts. And underneath it all, woven into the strongest transmissions, was fear. The most powerful signals Earth ever produced in those early years were not broadcasts of culture, but radar systems built to guard against nuclear attack. It is unsettling to realize that our first announcement to the galaxy was not of who we are, but of what we feared. The echo of our survival instincts became the loudest beacon of our presence. And survival, as it turned out, was never certain. In September of 1983, the fragility of Earth's signal became painfully clear. Tensions between the United States and the Soviet Union were at one of their peaks. Both sides had stockpiled thousands of nuclear weapons. The systems designed to detect an incoming strike were constantly on alert. On one night that month, alarms began to sound in a Soviet command bunker. The computers reported that several American missiles had been launched and were now streaking towards Soviet targets. If the report had been passed up the chain, retaliation could have followed within minutes. The Soviet arsenal was vast enough to destroy much of the world. The American arsenal was equally large. Civilization might have ended before most people even realized a mistake had been made. But the officer on duty, Stanislav Petrov, did not follow protocol. Something about the report seemed wrong to him. The number of missiles was too small. The ground-based radars showed nothing. He waited, choosing not to sound the alarm. His decision was correct. There had been no attack. The satellites had confused the reflection of sunlight on high clouds for the heat signatures of missiles. History turned on that hesitation. If Petrov had acted differently, the transmissions humanity had been spilling into space for half a century would have ended abruptly. Our bubble of detectability would have been cut short, its edge forever frozen a mere 50 light-years wide. To the rest of the galaxy, it would have looked like a civilization that shouted briefly and then fell silent. Another voice extinguished before it had a chance to be heard. That moment captures something essential about the search for life beyond Earth. It reminds us that any civilization capable of broadcasting into space must first pass through a narrow corridor of danger. The same tools that allow it to be noticed also give it the ability to erase itself. To survive long enough to be heard is not guaranteed. Even if a civilization does endure, its detectability is more fragile than it seems. Imagine that expanding bubble of Earth signals. Today, it stretches about 100 light-years in radius. At first glance, that seems vast. 100 years of transmissions, racing outward through interstellar space. But set that next to the scale of the Milky Way. Our galaxy is 100,000 light-years across. Our bubble, enormous to us, is barely a pinprick against that backdrop. Unless a civilization happens to be within that tiny sphere, it will never know we exist. And even inside the bubble, the signals are weaker than we often imagine. Every time the distance doubles, the energy is spread over 4 times the area. The farther the signal travels, the fainter it becomes, until it merges with the natural background hiss of the universe. Detecting it would require extraordinary instruments, perhaps more sensitive than anything we currently possess. There is another complication. Earth is becoming quieter. In the middle of the 20th century, radio and television poured energy into space without restraint. Towers broadcast in every direction. Signals overlapped, interfered, and wasted power. That chaos made us visible, but technology has changed. Fiber optic cables now carry much of our communication beneath the oceans and across continents. Satellites use narrow, efficient beams. Digital encoding hides information inside signals that to an outsider look like noise. From the perspective of the galaxy, Earth's lantern is dimming. This may be a universal pattern. Perhaps every civilization goes through a brief phase of loudness, a century or two when its technology leaks into the cosmos. Then, as it becomes more advanced, it grows quieter. Communications grow efficient, signals become invisible. Unless that civilization chooses to broadcast deliberately, it vanishes from detectability. If that is true, then the chances of overlap are far smaller than we might hope. 2 civilizations may exist in the same galaxy, even in the same region, but if their noisy windows do not coincide, they will never know each other. They will pass like ships in a dark ocean, each lantern lit for only a moment, each extinguished before the other has a chance to see. This problem of timing is perhaps the most haunting of all. Earth has been alive for 4 billion years. For almost all of that time, it was silent. Only in the last century has it become visible. That is 1/40,000,000th of Earth's history. If civilizations elsewhere follow similar paths, then most of the time they too will be invisible. Their signals may have come and gone long before we began to listen, or they may arise long after we're gone. The galaxy could be full of signals, but most may be echoes. still travelling through space long after their senders have vanished. If we ever detect one, it may not lead to contact with living beings, but to the memory of a civilization already gone. We may be archaeologists of the cosmos, discovering not companions but ghosts. And yet, we still send our own gestures into the dark. Not just accidental leaks, but deliberate messages. In 1974, the Arecibo telescope in Puerto Rico sent a 3-minute broadcast toward a star cluster 25,000 light-years away. Encoded within it were numbers, symbols of DNA, a sketch of our solar system, and the outline of a human figure. It was never meant as a conversation. Any reply would take 50,000 years. It was a statement, a marker, proof that we existed and wanted to be noticed. The Pioneer spacecraft carried small metal plaques engraved with the outline of 2 human beings and a diagram of our location in the galaxy. The Voyager probes carried golden records designed to last for billions of years, with greetings in many languages, music from around the world, the sound of waves, wind, thunder, and birdsong. They are drifting now in interstellar space, perhaps forever unseen, perhaps one day discovered. These attempts remind us that even if the odds of being heard are vanishingly small, we still choose to speak. The act of sending is itself meaningful. It says that we were here, that we looked outward, that we refused to let the silence define us. But the loneliness of our signal is still undeniable. For all our broadcasts, for all our gestures, no reply has yet come. Our bubble continues to expand, but it is faint, fragile, and perhaps already fading. Unless someone happens to be listening, with instruments far beyond our own, at exactly the right moment, it may pass unnoticed. This is the strange paradox of our time. We are more capable than ever of listening, yet we are quieter than ever in being heard. Perhaps this is true everywhere. Perhaps the galaxy is not silent, but filled with civilizations that are simply past their noisy windows, invisible to one another. If so, the silence we perceive may not be emptiness at all. It may be the sound of missed connections, signals passing like lanterns in the night, never overlapping. Still, there is something profound in knowing that for a moment, however brief, we are part of the chorus. Our voices are there, racing outward. They may fade, they may vanish, but they existed. And perhaps that is enough. In the end, the loneliest signal is not the one that goes unanswered. It is the one that is never sent. And for this short window in cosmic history, Earth has chosen to send. In the summer of 1950, a handful of scientists sat down for lunch at Los Alamos. It was a casual meal, the kind of gathering where jokes and side conversations drift across the table. They were talking about the possibilities of space travel, about rockets and the future, when the Italian physicist Enrico Fermi suddenly interrupted with a simple question. Where is everybody? The room grew quiet. Everyone at that table understood what he meant. The galaxy is ancient. The stars are countless. If life arises easily, and if intelligence is not impossibly rare, then someone else should have had time to spread through the stars long before us. They could have crossed the galaxy many times over. So why, Fermi asked, do we see nothing? No visitors, no evidence, no signs. That question has echoed ever since. Today we call it the Fermi paradox, the tension between expectation and reality, between the vast numbers that suggest company and the silence that greets us when we listen. The silence itself is not surprising. Space is enormous, signals are faint, and we have only just begun to search. But the scale of the paradox is unsettling. Even if interstellar travel is slow, civilizations could spread gradually, one star at a time, until entire regions of the galaxy were filled with life. Yet the skies remain quiet. One possible answer is that life is rare. Maybe Earth is exceptional. Maybe the chain of events that led from simple chemistry to complex beings capable of building telescopes is so improbable that it has happened only once in the galaxy. But there is another answer, one that many scientists find harder to dismiss. Maybe civilizations do arise often. Maybe the galaxy has been full of them. But something happens to prevent them from lasting. Something that keeps them from reaching out or from being noticed when they do. This idea is often called the Great Filter. Somewhere between the spark of life and the expansion of civilizations across the stars, there is a barrier. It may come early or it may come late, but it is enough to explain the silence. If the filter lies behind us, then Earth is unimaginably lucky. Perhaps the origin of a life is so rare that almost no planets manage it. Perhaps intelligence is nearly impossible, and we are one of the very few to cross that line. In that case, the silence is not ominous but precious. It would mean we are rare jewels in a vast and mostly empty galaxy. But if the filter lies ahead of us, the silence becomes more haunting. It would mean that civilizations commonly reach our stage, but rarely pass beyond it. It would mean that the path we are on, a path of growing power and fragile survival, ends in collapse more often than it continues. This possibility becomes difficult to ignore when we look at ourselves. In the middle of the 20th century, humanity created weapons powerful enough to destroy everything it had built. At the height of the Cold War, the combined arsenals of the United States and the Soviet Union held more than 70,000 nuclear warheads. The destruction they could unleash was almost beyond comprehension. For decades, civilization survived on the edge of a knife, dependent on the restraint of fallible leaders and the reliability of fragile machines. We know how close we came. The Cuban Missile Crisis in 1962 brought the world within days of nuclear war. In 1995, Russian systems mistook a scientific rocket launched from Norway for a possible missile attack. Only after tense minutes was the alert called off, and in 1983, as we have already seen, Stanislav Petrov refused to follow a false alarm that might have triggered catastrophe. At least 3 times in the last century, chance and hesitation stood between survival and silence. Nuclear weapons are only one of the filters we face. There is climate change driven by our own activity. Venus may once have had oceans and clouds like ours, until runaway greenhouse gases transformed it into a furnace. The same processes, on a smaller scale, threaten us today. The danger is not only gradual warming, but the possibility of feedback loops that spiral beyond our control. If civilizations across the galaxy commonly destabilize their own environments, it could explain why they burn out quickly, leaving behind no lasting signal. There are natural filters as well. 70,000 years ago, the Toba supervolcano erupted in Indonesia, filling the skies with ash. Some evidence suggests that the human population may have been reduced to only a few thousand individuals. Our species survived, but barely. Events like this are rare, but not impossible. Asteroids, supervolcanoes, nearby supernovae, the galaxy is filled with hazards. A civilization might endure for centuries and then vanish in a single geological heartbeat. All of these dangers help explain the silence. If civilizations are fragile, if their average lifespan as detectable societies is short, then we should not be surprised that we find no company. They would appear briefly, flare with energy, and then vanish. From a distance, their histories would blur into quiet. But not every explanation is about destruction. Some are about choice. It may be that civilizations choose not to speak. The reason could be caution. Imagine a galaxy filled with civilizations that know others may exist but cannot see them. Each one faces a decision: remain quiet or announce itself. To speak is to reveal your location. If the galaxy is safe, this is harmless. But if there is even the possibility of danger, silence may be the wiser path. This is the heart of what some call the dark forest hypothesis. The galaxy is a forest at night. Every civilization is a hunter, aware that others may be nearby but uncertain of their intentions. To announce yourself is to risk becoming prey. So each remains quiet, listening but never speaking, hoping to avoid detection. If this is true, then the silence we hear is not the silence of absence, but the silence of fear. There is also a darker extension of this idea. Some suggest that the silence is enforced. Perhaps long ago one civilization unleashed self-replicating machines designed to eliminate potential rivals. These hypothetical probes, often called berserkers, would spread from star to star, programmed with a single directive: destroy any technological life they encounter. If such machines exist, the first signal any young civilization sends might be the last. The galaxy would remain silent because the loud do not last. We cannot know if such ideas are real. They may be speculation, cautionary tales rather than actual dangers, but they capture the fragility of the situation we face. The silence of the stars is not meaningless. It tells us that something, somewhere, is limiting what we expected to see. Whether it is rarity, fragility, fear, or extermination, the result is the same. The sky above us is quiet, This is why the term that Frank Drake placed at the end of his equation carries so much weight. The length of time civilizations remain detectable, what he simply called L, dominates everything else. If L is long, thousands or millions of years, then signals should be everywhere. But if L is short, only a few centuries, then silence is exactly what we would expect. The galaxy could be filled with civilizations that never overlap, each one vanishing before the next becomes visible. It forces us to think not only about them, but about us. How long will we last? How long will we remain visible before we fall quiet? The silence of the stars is not only a puzzle about others, it is a mirror held up to our own future. Perhaps the most hopeful interpretation is that the filter lies behind us. Perhaps life itself is rare, and intelligence even rarer. If that is true, then we have already crossed the hardest barrier. The silence would mean we are unusual, maybe unique, and our challenge is simply to endure. In that case, we may one day fill the galaxy with our presence, not because others failed, but because they never existed in the first place. But the most sobering interpretation is that the filter lies ahead, that the silence we hear is the silence of civilizations that did not survive the stage we are entering now. If that is true, then the quiet skies are not comforting but foreboding. They are a warning, telling us that what comes next may be more difficult than we imagine. In the end, the great silence is not empty. It is full of questions. It asks whether we are fragile or rare. It asks whether we are reckless to broadcast or wise to listen. It asks whether survival is common or exceptional. And it asks most of all whether we will be among the civilizations that last. We look into the sky and we hear nothing. But the silence itself speaks. It tells us that the universe is not obligated to be filled with company. It reminds us that longevity is not guaranteed. And it leaves us with a choice. We can interpret the silence as absence and despair, or we can interpret it as possibility and work to ensure that our own signal endures. When we talk about the possibility of civilizations beyond Earth, it is easy to imagine them as loud, unmistakable, filling the sky with signals. But what if most of them are quiet? What if the real challenge is not whether they exist, but whether we can ever notice them in the first place? This is where the question becomes less about others and more about ourselves, because even as we search, we are beginning to realize that our own detectability may be fleeting. We may be passing through a brief phase in which we are visible, only to vanish again into silence. If that is true, then what we are experiencing now may be the only chance civilizations ever have to find one another. Think of it this way. For nearly 4 billion years, Earth was alive but invisible. Microbes, oceans, forests, animals, all of it unseen from the perspective of the galaxy. Only in the last century have we been noticeable, leaking radio waves, radar and television into space. That century is not even a heartbeat in cosmic time, and already the volume of our noise is dropping. Most of our communication now is carried by fiber optics, cables beneath oceans and across continents. Satellites transmit narrow beams aimed at specific targets, not broad scatter into the sky. Digital encoding hides information inside signals that to an outsider look like background noise. To the universe, Earth is growing quieter with each passing decade. The great flare of our radio age may already be dimming. This pattern may be universal. Perhaps every civilization has a noisy window, a brief span when its technology spills signals outward. A century here, a century there. Against the scale of millions of years, those windows barely overlap. Civilizations may be common, but they rarely catch one another in the act of speaking. If so, the silence we hear is not absence, it is missed connection. That possibility makes the search for unusual signals all the more urgent. Because if civilizations are only briefly detectable, then the signs may be faint, rare, and fleeting. What we are really searching for is not an ongoing broadcast, but an anomaly, something that doesn't quite fit. From time to time, we do find such anomalies, stars that behave in ways we cannot explain. One of the most famous in recent memory is KIC 8462852, often called Tabby's star, after the astronomer Tabitha Boyajian who studied it. The star began to dim in strange ways, losing up to 20% of its brightness for days or weeks at a time. No natural process we knew could explain it. Dust clouds, comets, stellar fluctuations, all were proposed, but none fit perfectly. For a moment, speculation turned to the idea of megastructures, enormous constructions built by an advanced civilization, perhaps to harvest energy from the star. The idea of a Dyson sphere, a vast shell or swarm of collectors surrounding a star, has been around for decades. Such structures, if they exist, would leave a signature, not in radio, but in light. The star would flicker or dim unnaturally. For a while, Tabby's star looked like such a candidate. Later data suggested more mundane explanations, but the mystery is not fully resolved. And whether or not the cause is artificial, the episode reminded us of an important point. If civilizations build on stellar scales, their presence might be noticed not in what they say, but in what they alter. Another star, Przybylski's star, adds to the mystery. Its spectrum contains elements that should not exist in nature, at least not in stable form. Some of the lines correspond to isotopes that decay in days or hours. Why they appear in its light is unclear. There may be natural explanations we do not yet understand, but anomalies like these remind us to keep an open mind. The universe may hold signatures we are not prepared to recognize. Then there are the fast radio bursts, sudden flashes of energy lasting only milliseconds, brighter than whole galaxies for their instant of existence. They were discovered only in the last 2 decades, and their origins are still debated. Most appear to come from distant galaxies, billions of light years away. Some repeat, most do not. Neutron stars, magnetars, black holes, all have been suggested as causes. But the sheer power and brevity of these bursts make them intriguing as possible candidates for artificial signals. If you wanted to announce your presence in the most energy-efficient way, a short, bright flash is one way to do it. Some theorists have even suggested that advanced civilizations might use such bursts as lighthouses, flashing at intervals, visible across cosmological distances. This idea is sometimes called the Benford beacons hypothesis, after the physicists who proposed it. Instead of broadcasting continuously, which would require enormous amounts of energy, a civilization could send rare, powerful pulses, perhaps once per year, or even once per century. These would serve as signposts, attention-grabbing flashes designed to be noticed, followed by silence. To us they might appear as one-off events, lost in the sea of natural phenomena. Only by watching patiently would we realize they were intentional. If this is true, then our current search methods may miss most of what's out there. We look for ongoing signals, steady transmissions, things that resemble our own broadcasts. But other civilizations may use methods entirely unlike ours. Neutrino beams, gravitational waves, even quantum entanglement have been suggested as possible communication tools. Each has advantages we cannot yet exploit. Neutrinos can pass through matter without obstruction, allowing messages to be sent straight through planets. Gravitational waves travel without interference. Quantum entanglement, if it can be harnessed, might allow for forms of communication we can scarcely imagine. To civilizations far ahead of us, our radio searches may look as outdated as smoke signals. This possibility, that we are searching in the wrong way, is both daunting and liberating. It reminds us that silence does not mean absence. It may mean we are looking with the wrong instruments, in the wrong part of the spectrum, or for the wrong kind of signal. The universe could be alive with communication, invisible to us until we learn how to notice it. But there is another possibility, stranger still. What if civilizations do not vanish through destruction, nor hide in silence, nor communicate in ways we cannot yet detect? What if they simply turn inward? This is the idea of transcension. Instead of spreading across the stars, civilizations may choose to compress. As technology advances, they may build ever more sophisticated simulations, virtual realities so complete that physical expansion becomes unnecessary. They might collapse into smaller and smaller spaces, focusing on internal exploration rather than external conquest. From the outside, they would appear to vanish. Their planets would grow quiet. Their stars would remain untouched. To us, it would look as though nothing ever happened. It is an unsettling thought, because it suggests that absence does not mean failure. It may mean success, but success of a kind we cannot see. Civilizations might survive for millions of years, thriving in forms that leave no trace visible to us. The silence, in this view, is not death but transcendence. Where does that leave us? For now, it leaves us in a brief, noisy moment. Our own window of detectability is already closing. The first century of our radio age may also be the last. Unless we make deliberate efforts to remain visible, Earth will soon fade back into quiet. Our lantern will dim, our presence will become invisible to others. This is perhaps the most haunting lesson of all, because if every civilization experiences this brief scream, a century or two of noise followed by silence, then the galaxy could be filled with lives and cultures we will never know. Civilizations could rise and fall by the millions, each one flickering briefly, each one vanishing before the next had a chance to listen. The silence we hear would not be emptiness. It would be the space between overlapping shouts, the pauses in a cosmic conversation too slow for us to perceive. And so we find ourselves at a crossroads. We can choose to send deliberate signals, to extend our visibility, to ensure that our presence lasts beyond this accidental century. Or we can retreat into efficiency, encryption, and inward focus, allowing our voice to vanish. Either way, our window will not last forever. It is worth pausing on what this means. For a planet 4 billion years old, a century of visibility is nothing, a blink, a fraction of a fraction, and yet, in that blink, everything we are has become part of the universe's story. Our transmissions are out there now, moving at light speed, carrying with them the evidence of a species that once looked up and wondered. Perhaps that is enough. Even if no one hears us, even if our shout is swallowed by the void, the act of sending is itself meaningful. It proves that we tried, that we were curious, that we refused to let silence be the only answer. But it also leaves us with a haunting possibility. If civilizations are only briefly visible, then perhaps we have already missed countless neighbours. Civilizations that shouted their presence long ago, whose signals passed by before we had the tools to notice. Civilizations yet to come, who will shout after we have already gone silent. The galaxy may be filled with voices, all of them passing each other in the night, none of them overlapping. For now, Earth's lantern is lit. Our bubble of detectability expands, and while it lasts, we listen, hoping to catch even a single echo from another. Because if the noisy windows of civilizations are as brief as they seem, then hearing one another may be the rarest miracle of all. For more than 60 years, humanity has been listening. Through static, through the hiss of cosmic noise, through the hum of our own machines, we have searched for something that might break the silence. No message has come, but the search itself has become part of who we are. One of the people most associated with that search is Jill Tarter. For 4 decades, she dedicated her life to scanning the skies, leading projects at the SETI Institute, and pushing the limits of what our instruments could detect. She often reminded us that we have only just begun. In her words, we have so far examined only a single glass of water from Earth's oceans. That is how little of the cosmic haystack we have sampled. With so much left unexplored, the silence should not discourage us. It should remind us how vast the search truly is, and the search continues. The Allen Telescope Array, a field of radio dishes in California, listens constantly for signals. The Breakthrough Listen project, funded in the last decade, has given SETI its most ambitious survey yet, scanning 1 million stars for even the faintest whisper. Every hour of observation adds to our understanding, ruling out some possibilities, hinting at others, expanding the map of what we know and what we still must explore. From time to time, the universe gives us puzzles that fuel our imagination. We think back to the WOW signal of 1977, that 72-second burst in Ohio that matched perfectly what an artificial signal should look like. It came, it went, and it never returned. To this day, no one knows what it was. Most likely it was natural, but we cannot prove it. That small fragment of data has become an icon of the mystery, a reminder that the line between noise and message is not always easy to draw. In 2017, another mystery arrived. Astronomers discovered an object passing through our solar system on a hyperbolic trajectory, the first confirmed visitor from interstellar space. It was given the name Oumuamua, a Hawaiian word meaning scout or messenger. Its shape was elongated, unlike most asteroids, and as it tumbled past the Sun, it accelerated slightly in ways that comets often do, but without the visible tail of dust or gas we expected. For a time, some wondered if it might be artificial, a fragment of a probe, a light sail, something left adrift by another civilization. The debate continues, with natural explanations competing against speculation. Whatever it was, it came and went quickly, a reminder that even if artifacts of others exist, we may only glimpse them briefly, never long enough to be sure. Other anomalies keep us on our toes. Strange stars that flicker without clear cause, fast radio bursts that flash with more energy than entire galaxies in the span of milliseconds. Most of these have natural explanations, or at least plausible candidates. But their strangeness keeps our imaginations alive. They force us to admit that the universe may still hold surprises, and that among those surprises might be the signatures of intelligence. When we speak of those signatures, we sometimes use the word techno-signatures, the broad category of traces left not by natural processes, but by technology. They might be radio signals, but they could also be waste heat from vast energy structures, artificial patterns in starlight, unusual chemical fingerprints in planetary atmospheres. Searching for techno-signatures is, in a sense, archaeology at interstellar scales. We are looking not just for voices, but for traces, artifacts, scars left by civilizations that may no longer exist. The idea is humbling, because even if we do find such a trace, it may not lead to conversation. It may lead to realization, the knowledge that someone else once was, even if they are gone now. In that sense, SETI is not only a search for company, it is a search for memory. Philosophy inevitably enters the conversation. Some wonder if the silence is not natural at all, but intentional. The simulation hypothesis, for example, suggests that our reality may itself be a construct, and that the absence of signals is a feature, not a flaw. If we are inside a simulation designed for certain conditions, then the quiet of the galaxy may be deliberate. The rules of the program written to prevent discovery of neighbours. It is speculation, yes, but it highlights how deeply the silence unsettles us, enough that we imagine not only civilizations, but the fabric of reality itself conspiring to keep us alone. Others suggest that civilizations may change in ways that make them undetectable. As technology advances, they may abandon physical expansion for digital existence, compressing themselves into simulated worlds, pursuing richness of experience rather than conquest of space. To outsiders, they would vanish. Their stars would remain untouched, their planets unmarked. The galaxy could be filled with such civilizations, invisible not because they died, but because they transcended. Whether by simulation or transcension, the result is the same: quiet skies. The silence becomes not the mark of emptiness, but of transformation. Civilizations may continue, but in forms that leave no footprint we can perceive. For us, the question is not only whether others exist, but how long our own voice will last. Our window of detectability may already be closing. The century of radio and television leakage may be a brief flare, soon replaced by efficient directed communications that do not escape into space. Unless we choose to send deliberate messages, powerful intentional beacons, our presence may fade. The bubble of Earth's noise will continue to expand, but its edge will grow fainter, lost against the background. To future civilizations, we may be invisible. This fragility makes our current moment feel precious. For a brief time, we're here, speaking into the dark, hoping for an answer. Our voices are racing outward. News bulletins, radar pulses, encoded messages, even the carefully designed artifacts we have launched on spacecraft. The Pioneer plaques, the Voyager golden records, small symbolic gestures cast like bottles into the cosmic ocean. They may never be found, but they exist. They are proof that we wanted to be heard. The Voyager records in particular carry a poignancy that is hard to overstate. Encased in gold, designed to survive for 1 billion years, they hold greetings in dozens of languages, the music of Bach and Beethoven, the sound of whales, the laughter of children. They drift now in interstellar space, farther than any human object has ever travelled. Long after Earth has gone quiet, those records will still be out there, silent ambassadors of a species that once looked up and wondered. Carl Sagan, who helped design them, understood their significance. He also gave us another image, one that may be the most powerful reflection of our place in the cosmos, the pale blue dot. In 1990, as Voyager 1 was leaving the solar system, it turned back its camera and took a picture of Earth from 4 billion miles away. The result was a tiny speck, barely a pixel, suspended in a shaft of sunlight. That dot, Sagan reminded us, contained everyone we have ever known. Every king, every peasant, every mother, every child, every hunter, every farmer, every soldier, every saint, every sinner. All of human history, all of human striving, condensed into a mote of dust in a vast, indifferent void. When we look at that image today, it resonates even more deeply. Because not only is Earth a pale dot, it is also a brief signal. For just a century it has been speaking. For just a moment in cosmic time, it has declared its presence. And the question that lingers is whether that signal will last. The Drake equation never promised us answers. It only gave us a framework to ask the right questions. And the last of those questions, the one that made the scientists at Green Bank fall silent in 1961, is the same one that haunts us now. How long do civilizations endure? How long do they remain loud enough to be heard? As we close this journey, we return to that question. Because everything we have explored, the abundance of stars, the likelihood of planets, the resilience of life, the possibility of intelligence, all of it comes down to longevity, to whether signals overlap, to whether voices carry far enough, long enough to meet. We may never know the answer. The silence may continue for centuries. Or one day, suddenly, a signal may arrive, breaking the quiet, reminding us that we are not alone. Until then, we listen. We send our small messages. We let our voices leak into the night, not because we are certain of reply, but because it is what we do. Perhaps, as some have suggested, the very act of listening is what keeps a civilization alive. To look outward, to imagine others, to hope for company. Perhaps that curiosity is itself the survival trait. Perhaps the search is not only about them, but about us. Tonight, as our planet turns and night falls across one hemisphere after another, radio waves carrying fragments of our lives are slipping past another star. They are faint, fragile, easily lost in the noise, but they are real. They are our song, our story, our proof of existence. Someone may be listening, or no one at all. Either way, for this brief moment in cosmic history, Earth is singing into the dark. Thank you for watching.